Hi everyone, my name is Adeyemi Balogun and with my colleagues Manish Kumar and Reza, we will be taking you through a presentation on the design and simulation of a PV system to meet the energy needs of a solar electric rickshaw. This is a course under the supervision of Dr. Tariq Iqbal. In this presentation, we will be looking at the overview of projects, the introduction, the methodology, the dynamics, and the summary of the entire project. So let's get right to it. For this project, we have looked at a rickshaw. The alternative energy we have proposed is the solar energy. This project is conducted in the Simulink environment in MATLAB. The location of study is Gujarat, and the yearly average irradiation of this location is 5.54 kilowatt hour per day per meter squared. Moving a step further in this presentation, our world is changing because of global warming due to the emission of greenhouse gases, which is largely attributed to the burning of fuel, making transport sector a cause of concern. Now, to mitigate these challenges, we have seen different form of rickshaw introduced to reduce the noise and pollution. Compressed natural gas and liquefied petroleum gas rickshaw have been introduced, but due to the shortage of these fuels, these vehicles have not gained popularity. Now, a pure electric auto rickshaw would have been ideal for pollution and energy use, but commercialization is limited by the energy storage capacities of currently available batteries. So why e-rickshaw? Well, primarily the source of energy is from the sun. It is also a key alternative to this fossil fuel, and then it is cleaner and easier to maintain. Now I will briefly run through the methodology. In this section we look at the schematics of the e-rickshaw. Now the e-rickshaw consists of the solar collector, the DC to DC power electronic converter, we have the battery unit, we have the power electronic driver, we have the AC to DC power electronic rectifier, and we have the wheel hub motor. So the solar collector is just the PV panel that collects solar energy from the sun. The battery unit entails the battery pack and the BMS, that's the battery management system. The power electronic converter is just like our boost converter. In that section, we have the boost converter, we have the inverters, we have the appropriate controllers with algorithms, and what this section does is to feed electricity energy from battery to the motor. We have our AC to DC electronic rectifier, and we have the power electronic driver. And in this section, we have used the permanent magnetic synchronous motor because research have shown that this motor is quiet and efficient. Worthy of mention is also the transmission section, which consists of the clutch, the gear, and what this section does is to transmit power from the motor to the wheel. In this slide, I will briefly discuss about one very crucial concept that was used in the converter section of the project, which is the MPPT. MPPT is just the technology that can be used to optimize the PV output. It does this by basically matching the PV to the battery. So like we can see on the slide, MPPT is important for efficiency. There are three main methods in literature, but I won't be getting into that because of time. The normal charge controllers we have, they can get you, the best you can get from them is about 70%, but MPPT can deliver even up to 90%. And the control mechanism for MPPT is by the duty ratio. So underpinning the previous slide, as we can see the comparison between the PWM converter and then the MPPT converter. When trying to evaluate and model the performance of a rickshaw, Some factors like friction and wind are important in the analysis. Now, other factors that should be considered include the rolling resistance, which is the frictional force experienced between the tire and the ground while the vehicle rolls. The grading resistance talks about when the vehicle is climbing a slope. The aerodynamic drag is associated with the wind. The acceleration resistance is just.
Now, to evaluate the energy required by the electrical motor to drive the rickshaw, we have considered a different complication parameter or different dimensions and parameter for the e-rickshaw, and those are the vehicle dimensions, passenger weight dimension, gear ratio, uh, the mass of the vehicle, acceleration due to the gravitational resistance, grade angle, air density, drag coefficient, the velocity of the vehicle, total inertia constant, front area, radius of the wheel, time of acceleration and efficiency of the motor. The most important observations here is the vehicle dimensions. It is 2.779 by 0.99 into 1.75 meter, and that is enough to accommodate the 3 to 4 passengers, and the vehicle mass is 360 kilogram, and acceleration is 0.54167 meter per square, and speed that can be achieved, the maximum speed that can be achieved is 6.5 meter per second. We here calculated the power requirement by the e-rickshaws electrical motor, and on the flat road, the energy required by the electrical motor is 1.951 kilowatt. In case of the slope road, it is 2.206 kilowatt. So, the rated power 2.2 kilowatt PMSM motor is sufficient to drive the electrical rickshaw, and we have considered this motor, which have power output of 2.2 kilowatts, rated voltage 220 volts, rated speed is 1500 rpm, frequency is 50 hertz, and number of poles is 4. This motor is enough to drive the considered e-rickshaw. Now, battery is very important as it provides energy for the optimal period. Battery type, capacity, operation. However, while considering the weight are crucial in selecting the battery input energy requirement is calculated by the given equations, and battery string ampere is calculated by calculated voltage hour by dividing the calculated voltage hour by the rated voltage of the string. Here the configuration for the harvesting the solar energy for the electrical rickshaw is shown in the figure. Here solar panel output voltage and current are continuously measured, and with the help of the any MPPT algorithm, the measured voltage and current information is used to operate the solar panel in a way that they can deliver a maximum power. So the DC to DC converter output voltage is at a point where the solar can deliver the maximum power, and this is used to drive the motor as well as to charge the electrical battery. Now here, as for the PV output voltage, and electrical vehicle motor input voltage, and the battery voltage, we have designed DC to DC buck converter which have output voltage of 60 volt, input voltage is 60 to 72 volts, and our nominal output current is 45 ampere, and rated capacity is 2.7 kilowatts when it operates at maximum power level. So when the PV receive maximum irradiation at a site, in that case the output power of the buck converter is 2.7 kilowatts, and a rated energy at a rated capacity, the e-rickshaw energy requirement is 2.2 kilowatts. So even when the EV is running at a rated speed and a load, and when it receives the enough energy from the solar irradiations, then it can even in that case also it is able to charge the battery. Now the circuit configurations of the MPPT converter, which have PV cell, the buck converter, and the load is shown in the figure. So it's a Simulink model in the MATLAB Simulink, which have PV panel, DC to DC buck converter, MPPT algorithm, electrical battery, and different measuring points. Here we can see the MATLAB Simulink results. Here the output power, and the current for the different irradiation is showing. is shown in the figure, and we can see that with the change in irradiation, there is considerable change in the output current and the power. But it is noted that the change or deviation in the voltage with the different irradiation is quite small. And we can also see the MPPT output voltage and current for the rated. Here is logic-based charge controller that is developed in a MATLAB Simulink. We created a different file as compared to previous MPPT-based controller-like model. The reason is the switching frequency of the buck converter is quite high, so step size is quite small. In this case, we need a large step size to simulate this model. The reason is the charging the battery required quite long period of time, and the battery is normally connected to the MPPT, but when it reached to predefined 96% SOC level, then it get disconnected. Here the MATLAB Simulink is also the battery charge controller. Here battery is charging from 60% state of charge to reach a 90% state of charge. During that period of time, you can see the change in the voltage and current, and it takes a considerable time to charge to reach a 96% state of charge level. Here battery is connected with the load, and the load is drawing the power from the battery, and the battery state of charge is continuously monitored, and the battery state of charge reaches 60%, then load is not allowed to draw the power from the battery, and the battery output is disconnected from the load. Here we can see the battery state of charge, voltage and currents, while the load is continuing drawing the power from the from the battery. And when the battery state of the charge reaches 60%, it is automatically disconnected by the discharge controller. Overall, we designed and developed a self-solar powered e-rickshaw, and we also developed a dynamic, mechanical, and